Hello, my name is Al Newman from Technical Consultants Incorporated, Longboat Key, Florida, and I'll be your guide to the Geometric Dimensioning and Tolerancing Applications 1 program. This program is an advanced study in geometric tolerancing. It goes beyond the basics. It takes the basics, and we're going to take the basics of geometric tolerancing and apply it to actual parts and assemblies. In fact, here's a problem in one of our project where it's a mixer assembly, and it's composed of a number of details, and all of these details will have to have geometric tolerancing applied. Now, the students will have detailed drawings of all of these different parts. We'll have an assembly showing all of the parts, how they fit together, and a functional requirements. And then the engineers, the designers, the draftsmen, the manufacturing people will have to apply geometric tolerancing to these parts. And you can see that we have a variety of different parts, and in some cases, they'll also have to do a tolerance stack up to make sure that they meet the functional requirements. So applying the geometric tolerancing, they'll have to establish a datum reference frame. They'll have to establish any form or orientation or location tolerances. They'll be applying profile tolerances to surfaces and position tolerances to holes, slots, tabs. There'll also be a big discussion on modifiers, data modifiers, make sure everything is properly applied. So the program will work something like this. I'll start off, give the students the problem, explain the functional requirements. There'll be something in the beginning of the unit to be able to read over. And once they understand the problem, it's very clear, then they'll be given the task to go in and tolerance the parts. Ideally, they should be in work groups. So gather a group of 3 or 4 or 5 engineers together, mix them from manufacturing, quality, and design, and manufacturing, and try and solve the problem and apply the tolerancing as necessary. Afterwards, I'll come back and give a solution to the problem. Now, at the beginning of every problem, there'll be a target. For example, they'll have to meet certain requirements, a coaxiality requirement or an alignment requirement, and that'll be their goal. At the end, to make sure that they met their goal, they'll be required to do a little tolerance stack and analysis on the parts. And then, if necessary, have to reallocate the tolerance to make sure they meet their needs. Now, in this program, there's a variety of different parts. And the variety of different parts will be a mixture of machine parts and fabrications and sheet metal parts. And these will come in modules, so the students will apply the tolerance into these modules, and they can be done in units. They don't have to be done all at one time. Now, there's some companion programs that you should know about that accompany this geometric tolerancing also. And these are separate programs. One is the Geometric Tolerancing Fundamentals program. It's important that the people understand the geometric tolerancing fundamentals before they enter this program. And this geometric tolerancing program is available, and it's available on DVD. We have video and PowerPoint, and we also have student workbooks on the subject. Now, there's also a geometric tolerancing stacks program. And a stacks program talks about the fundamentals of stacks and shows you how to do tolerance stacks on individual parts. The ideal situation would be to view the stacks program and the applications program at the same time and have the engineers mix problems from one to the other. So you're not just all doing stacks or just doing applications, and you learn the stacks while you're doing the applications, a step-by-step approach. In any event, I think that the students will find it to be an exciting project to do. Each one will be a little bit different, and you can pick and choose the problems in any order that you want. You'll find out that there's going to be links to each different project, and the students will begin their project, and then afterwards we'll see the solution. The solution will also be in the back of the workbook. Every student should have a workbook and follow along with the workbook. So if you have any problems, there's a phone number there's an email where you can reach me. Sometimes I travel a lot, on the road a lot, but I'll try to get back to you as soon as I can. So I wish you luck, and good journey through the Geometric Applications program. I hope you have as much fun working the problems as I did putting them together. So good luck to you on the program. The first unit we're going to be in is the grommet assembly. So everybody should have your workbook and follow along with the workbook. Some of the graphics that we have here are a little small, so it will help if you have your workbook and you can look at the screen and be able to look at the workbook at the same time. There's going to be some problems, some parts where I'm going to give you an assembly and I'm going to give you some details, and then you have to apply the geometric tolerancing. do the best of what you know on geometric tolerancing, and afterwards I'll come in and give you a good possible solution of how the part works. So let's get started. Let's work on our first problem. So the first one we have is the grommet assembly. This here is Unit 1. Now this grommet assembly, how it works, what we have is a bulkhead, and this is this orange bulkhead. You can see the orange bulkhead in this side view. And we have a large vessel that has a series of these bulkheads, and we have cables and wiring that goes through from one bulkhead to the other. As it goes through the bulkheads, we have to be able to seal up the hole that the cables come through. If you notice, this here is our bulkhead. You see I have a hole. It's an oval-shaped hole in the bulkhead, and these cables are coming through. Once the cables come through, we need the large hole because it has connectors on the end of it, and then we have to seal up this hole. So we have this grommet assembly that is two identical pieces. They're two identical pieces, and what they do is that they come around this cables and then bolt to the bulkhead and seal the hole up. Now there are some design requirements that have to happen here. We have some design requirements that said the gap, when these two parts come together, you see that gap right across there, that may not exceed 10 thousandths. The clearance holes in the bulkhead, this is the size of them. There are 3 of them. We have a 406 plus 15 minus 2. Those are the holes in the bulkhead, and they're positioned within 29. Now, in this gap over here, we have a gap. We may not exceed a gap here of 10 thousandths. And if we take a look in the side view, this gap over here, that has to be a maximum gap of 12 thousandths. Now, on the bulkhead already, this bulkhead, we have a flatness tolerance of 5 thousandths. And the maximum gap between the bulkhead and our parts must not exceed 10 thousandths. So those are some design requirements we have. They're worried about any sparks, anything coming through, or any debris coming through those holes. So it has to be sealed. It's somewhat of a clean environment. So I think the first thing I ought to do is show you how the part works. And I have a little video clip here that I would like to show you. Now this video clip shows the two parts. You see here they're coming together. You notice the circles cut out on each part. Those are identical parts, they're just flipped over. They're going to come around and they're going to seal over those cables. And once they seal over to the cables, you notice up on top we have to have our gaps controlled all the way around to make sure our gaps according to the drawing that we saw earlier. And here the parts are going to come together. You see I'm going to put the bolts in. You see they're going to come around. I'm going to put the bolts, and on the back side, put the bolts through and we tighten up the nuts. Let me just show you that one more time so you can see it. There's the two pieces coming together. They seal around the cables. We're going to put the bolts through, the 3/8 bolts, put the nut on, and that's our assembly. Now, here's back at our assembly. Now, when we put those pieces together, let me remind you, we had a gap over here, couldn't exceed 10 thousandths. We had a gap over here that couldn't exceed 10 thousandths. We had to seal against the surface. It couldn't exceed any more than 10 thousandths. And we had a gap over here that had to be a max gap of 12 thousandths. Now you can take a look at your drawing in your workbook, and this should have all of this information on here. It's going to be your job to be able to look at everything and make sure you meet these final requirements when the product is completed. Now, what I also have here is, let me show you a model I have of the part. This is the model. This is my bulkhead. Picture of the bulkhead, and I remember how it works is I have these cables that we be going through the bulkhead, and we're interested in sealing up this hole. If we're interested in sealing up these holes, I have these parts. You see what it does is that it goes around, comes around those parts over there. This thing comes around on the other side and seals up that hole. And once it seals up the hole, then we tighten it up. Now it's interesting when you take a look at this part, when these two parts. These two are identical parts. See how they come together? They're an identical part. So it's not a right and left-hand part. You see they're both the same. All you do is you just take the part and you turn it around and assemble it with the mating part here like this. That's a rather ingenious design. I thought it was pretty clever the designer who come up with this one. Now this is interesting. Take a look at our drawing here. This is the engineering drawing on the part. And if you notice on the engineering drawing, we have a line here, and there's a line that comes all the way across. And when you look at this engineering drawing, it looks like this is the same surface, this line. You see that line? Comes right across here. And it's a little deceiving on this picture. Now let's take a look back at the model. Notice on the model, you see there's the line that we have right here. Line comes all the way across. But really, those are two surfaces. You see, I have this surface here, and then I also have this surface here. Those are two distinct surfaces. Those are not the same surface. So when I show the line, it looks deceiving. It looks like that line goes all the way across, but there's a surface underneath here, then there's the surface over here. And you notice the way the two parts work is that when the two come together, the two surfaces match up. So it's this top surface here comes up and lines up on this surface, and when you come onto the other side, it does the same on the other side over here. That's how the parts go together. So a little deceiving. You might have a model there with you, and you can take a look at that model and examine it a little bit closer if you have the models of this particular part there too. Okay, now what it is, let's take a look back at our drawing. It's going to be your job to be able to tolerance this part. Apply any geometric tolerancing on this part to make sure that you incur a functional fit and meets all design requirements on the first page. Now, up on top here, I put a little drawing of the assembly to show you how the parts go together. Remember, that gap over there, I think, couldn't exceed 10. That gap over there couldn't exceed 10. And then on the side, remember, with the two parts, that couldn't exceed any more than 12 thousandths. So what I would like you to do is apply geometric tolerancing to this part. Now, you should be an expert. You've went through the fundamentals program, knowing what you know. How would you apply? So the first thing, what I'd like you to do is select datums. And we're going to go in an organized fashion here to keep all of us together, to keep us all together on the application projects. We're going to work in these three basic steps. This is the steps that I would use if I was tolerancing a part, how I would go about it in a procedural manner. Number one, what we first would have to do, you don't want to go around and start applying any flatness or parallelism or putting position on. First, number one, what you want to do is establish the datum reference frame. Establish the datum reference frame, the DRF. In other words, establish the leaders. Call out the leaders. I want you to select datums, features in an order of precedence. The primary datum, the secondary datum, and the tertiary datum. Number two, what we'd like to be able to do is qualify the datum features to the datum reference frame. And what I mean by that is you want to qualify the leaders. Apply any form, orientation, or profile or location tolerances necessary relating the datum features to the datum reference frame. So first, you see what we do is we're going to establish the datum reference frame, establish the skeleton, where everything is going to come to. This is your groundwork. Relate all the features to the datum reference frame, and then following that, we're going to relate the remaining features to the datum reference frame. In other words, relate the followers. And you're going to apply any location tolerances or form or to the remaining features. And we're going to do it in these three steps, I think, at least initially, to keep us going. Okay, you'll see what I mean here as we get along. Okay, now on this part, I'm going to give you a few minutes knowing how they work. You take a look at that assembly again. And an ideal thing would be maybe some of you go into work groups. Maybe 3 or 4 of you get together and you look at this assembly. You talk about how it fits, how it works, how it goes together, and then based on what you know on how this part works, you're to apply the datums. Now, what I'd like to do, at least initially, is we're going to start off, and I'm just going to have you apply the datums first. Select the datums where you think they should be for these two parts going together. And once you select the datums, then what I want you to do is apply any perpendicularity or parallelism or form to relate the datum features. And then at that point, just stop. Don't go any further, because if you pick different datums than I did, we'll be so far apart that we won't be able to come together again. So I would like to give you this problem. You go in and you select the datums and qualify the datum features with flatness or perpendicularity, whatever you think, and then we'll come back, turn me back on, and then we're going to continue on. But we're going to just start with the datums here first. So let me give you a couple minutes. You, in your work groups, select the datums and qualify the datum features, and then turn me back on, and I'll come right back to you. All right, I'm back. Here I am. I hope that you've had a chance to apply the datums. That's going to be the first step, remember, in the establishing the datum reference frame. So number one, this is what I did, is I established that face as datum A. I established that face as datum A, and the reason I thought that that was datum A, if you take a look at my models, take this part and it matches up to the bulkhead, it mounts tight up against that face. If it mounts tight up against that face, I saw that as the primary datum. It mounts tight up against there. Now you might say, well, you said, well, yeah, that part mounts up, But this one, when it goes on, it mounts on the other side. Why didn't you pick the front face? Well, why I didn't pick the front face is I guess I could have picked the front face just as well as the back face, but you notice I saw the back face being longer, so I selected that as my primary datum. If I have a choice between a long one and a short one, I can't decide, I would just go for the long one. So that was my primary datum. All right, now let's take a look back at the graphic. Number 2, what did I select as my secondary datum? And my secondary datum, I call that surface off as datum B. I call that one off as datum B, and I call that surface off as datum C. Now, why did I do that? Well, this is what I thought. When the parts were coming together, you see how they're coming together? I take these two parts and I put them together. And first of all, they're coming together on the bulkhead, so that was my primary face. And then when they came together, you see how they're going to come together here, and I push them? You see how they locate one to the other? You see what I'm going to do is I'm going to push it tight up against that face. You see it comes right up against that face. That I call as my secondary datum. And then what stopped the part up and down, what I thought is it was going to be, well, I could have picked this top face up here, I could have picked this one here, and what I did is I picked this as my secondary, my tertiary. I picked this one as my secondary datum because that was the longer one. Now, I suppose I see sometimes people say, well, why not just pick the holes as your datums? And I suppose you could. You could pick the holes as datums, right, and then locate the surfaces. But the problem here that I thought is if I pick the holes of datum and I call those holes 0, then I'm going to have to come and tell you how much this face can be off. And I don't want this face to be off. The faces come on, right? I want the faces to come up tight. That's where they mount. They mount up tight against those faces. All right, the next step that I had to do was qualify the datum features. Remember, that was the second part. Qualifying the datum features, this back face, that's where it mounted up to the bulkhead. I put a flatness on this face. And I put a flatness on here that has a flatness within 5. Now, why a flatness within 5? If you remember, the requirements on the bulkhead is we couldn't have a gap here any more than 10 thousandths. And if we couldn't have a gap any more than 10 thousandths, remember on the bulkhead I had a flatness within 5. This one I had a flatness within 5. At worst case, that could give me a gap within 10. That's where that flatness came. Now, next datum. I had to qualify datum feature B. Now remember, sometimes people say, why do you need flatness on a datum? It's a datum, it's 0. Well, the datum is perfect, right? The datum is the theoretically perfect plane, but the datum feature comes in contact with the surface. So that's what I have to do is apply that surface. Now, let's take a look at the call out that I placed on there. I put a profile on. Now, why did I put a profile on? You would think that it would be just a perpendicularity. Well, a perpendicularity in this case here wouldn't work. And why a perpendicularity wouldn't work is because if I'm talking about these faces here, and there's 3 of these faces, you see, 1, 2, and 3. If I put a perpendicularity, you know how perpendicularity works. This surface would be perpendicular, this surface is perpendicular, and this surface is perpendicular, but perpendicularity doesn't make anything in line. It just says this is perpendicular, so this may be perpendicular out, this may be perpendicular in, this may be perpendicular out. So by putting a profile on, I have a tolerance zone, and a tolerance zone is a band of tolerance. Well, let's see if I can draw that band of tolerance here. It says that I have a perpendicularity zone, and the perpendicularity zones are in line. So I'll show that tolerance zone, and it's kind of hard to see there, but there's my tolerance zone. I have a band of tolerance, and the surfaces then have to fall someplace inside of that zone. And again, why I showed a tolerance there of 5 thousandths was because, remember, the mating part comes up to this, and in this area right here, we couldn't have a gap any more than 10 thousandths. So I put profile on this within 5 thousandths. The other one had 5 thousandths. That's going to give me a max gap of 10. Okay, let's take a look at next what I did. The next one that I did was this surface here. And this one here, now I could put a perpendicularity on that one because it's only an individual feature, right? Now, if you don't remember this profile, remember you have to take a look back in the fundamentals program, and I think you'll find this information about this in the fundamentals program I think it's unit 12 in the fundamentals workbook. Okay, and here's what I did is put a perpendicularity on here. Now, I put a perpendicularity, and I said that this was to occur between A and B. There's point A and there's point B, because you remember these are 2 different surfaces. This is the surface that's behind. This is a shelf that comes out forward. And I suppose if you put a perpendicularity on, people would say, well, it's not for both, but just to make sure that nobody thought that that perpendicularity goes all the way across, I just put a note down here and I said this perpendicularity, it occurs between A and B. Now if it occurs between A and B, then you see I have a gap there no more than 5 thousandths. So when I take the two parts and put together, I should have a max gap there of 10 thousandths, 5 thousandths on the one and 5 thousandths on the other. All right, so we've got our datums now, and if you, well, let's see if I can draw that datum reference frame. The datum reference frame, if I was to draw it, this one here establishes our leaders, and the leaders, let's see, our datum, it looks like it's going to be this face. All right, that was the datum here, and then it was also this face over here. Right? This is the origin of the coordinate system, right? And you notice that when we put this profile on over here, what that does is it allows this one to be off a little bit, allows this one to be off, allows this one to be off. I have this tolerance zone here. It's really not a plane that goes all the way across because there's only 3 surfaces. That zone of tolerance right there was 5 thousandths, right? And all of those zones are hooked together. Perpendicularity wouldn't hook them together, so I used a profile there. This one here I used a perpendicularity, so it's possible that this surface could come in something like this right on the datum feature. And it could be off no more than 5, but when I put my mating part on there, that's no more than 5. And remember, we had to have a gap of 10, so that's where this 5 thousandths came into play. Okay, this established our datum reference frame. So this is the first 2 parts of the requirements that we had to do. Remember, establish the datums, primary, secondary, and tertiary, that's what we did, and then we qualified the datum features by any flatness or perpendicularity or position that was necessary. And now next what we have to do is we relate the features. So we want to have the following features come related to this. So I'll tell you what, let me give you a minute. You select those datums, and now I want you to put any position on the holes or location on the surface. We need to be able to, remember, maintain a gap over here with the mating part that comes in here. Let me give you a couple minutes to come in and put your remaining tolerances on here, and you tolerance this the best that you can, and we'll come back in just a minute and see what you did. Well, welcome back. I give you a chance to apply the tolerancing to the grommet. I wanted you to do the calculations on those holes and make sure those holes fit with the mating part. Remember, when you're doing these, I don't want any just XXX in the way of tolerances. I want the drawings to be very neat. I want to be able to see just the way you would put them on a drawing, neat. I want all the feature control frames. I want all the diameter symbols. I want the modifiers. I want everything. I want the datums properly put on. I don't want any scribbling. I want it to be able to look really nice so everybody can see it. And then if you have any trouble with how to put the datum symbols on, remember, you should have along with you is the fundamentals workbook. You can look at that as an example, and you see how I did it in my examples, or you could have the ASME Y14.5 standard, how those datums and how those feature control frames are applied, and then you're going to do it on yours, and I want you to be very neat. So if you've been a little scribbly to this point, from now on, I want you to be very neat, so it's very legible, everything can be seen. You know, if you have a pen, get rid of that pen, get a pencil, get a big eraser, and make it really nice. All right, let's go on. What I did on mine is, first thing I did was I called all the dimensions basic. And all of the dimensions on here, rather than putting boxes around everything, I just said, unless otherwise specified, all untoleranced dimensions are basic. Make them theoretically exact. And that's the way that I do it, is I use profile tolerancing on here completely. Use it right to its fullest extent. All right, the next thing is we have to apply the tolerances. So the first thing what I did is I came in, and I'm going to go after the most important things first. So do you notice that this surface, when the 2 parts came together, that surface there, that couldn't be exactly in line with this feature, because if it was exactly in line, we wouldn't be able to get in. So this part has to be on that line, or it has to be down, right? So the way I did it is that I showed them in line. They have a basic dimension of 0, and if they have a basic dimension of 0, then I put a unilateral profile on it. And I said that surface has to be on that line, or it could be down by 5 thousandths. Now, I think I've explained to you before that I don't really like the unilateral tolerance too much. It's sometimes hard to be able to tell. You see that little line over here? That means it's a unilateral. When it's a unilateral, I will sometimes underneath the feature control frame put a note underneath there to make it larger, that it's unilateral towards metal, so it's very easy to see that you can see that it's going in one direction. Because sometimes this unilateral is hard to use, and sometimes in manufacturing, if they don't see anything, they're going to try and make it right to the line, and you notice that the line is really halfway in between. And then you got the problem of the model. Where you put the model? You put it at nominal, or do you put it at the basic? So I don't really like to use the unilateral, but in this case here it was for training purposes. And the only other alternative I would have had to do is I would have had to show this line 2.5 thousandths down below this line, and you wouldn't have been able to see it for training purposes. So I thought for training purposes I'm just going to use a unilateral, and it's another tool in our toolbox, and there's some cases you use it, so that surface is down. And then underneath here I said that that was between B and C. There's my point B, there's my point C, and that unilateral tolerance applies here. And that was 5 thousandths. The mating part would have 5 thousandths. That gives me my gap of 10 there again. All right, I'm going to go in after the most important things first, so let's take a look at what I'm doing next. The next thing is I came in and I located these holes. Now, there was 2 holes on this part, and they matched up to the bulkhead. Remember, there was 3 holes on the bulkhead, and it happens to be the same size hole. Now, how did I calculate that 29 in there, that 29 position? That was done with the floating fastener. If you remember, we reviewed those floating fastener formulas in the beginning, in the introduction to this, and this is how it was done. The floating fastener, to do those calculations, I would take the MMC of the hole. So here's my hole. The smallest hole is a 404 hole, 406 minus 2, 404, and then I took the MMC of the screw. And if I have a 375 screw, a 3/8 diameter, the major diameter would be 375. If you had an M10, for example, the major diameter on a metric would be 10 millimeters. So in this here is the largest you could get is 375. The clearance I had was 29, and since this is a floating fastener formula, we had nuts and bolts, I was able to give 29 to this part, and you notice on the bulkhead we had 29, so I could assure that these would fit. Also, I put maximum material condition in here, and maximum material condition, you know what that allows? It says that as these holes get larger in size, you can be off position a little bit more. And I thought that was fine. The holes don't locate it. What you do is you take these 2 parts and you push them together, and once they're put together, then you tighten up the bolt, and it clamps the part down. So it's just a clamping force of the bolt against the face that holds the parts together, right? So if the holes were a little larger, the faces is what really holds the parts together. So that's why I thought that I could use maximum material in there. Okay, next what I did is I applied a profile tolerance on here. You see that was my datum back here, that back face, and I said that was 247 away, and then I applied a profile tolerance, and I said that surface has to be profiled within 4. Now if that's profiled within 4, you know what that does is it's really doing something like this. I have a profile tolerance, and my profile tolerance, well, first of all, this is my datum. The datum is this face back here, right, that contacted on the high points. Not too good at straight lines here. And then it says profile within 4. So it says 247. When I put a profile of 4, what it's really saying is that surface can come in to, or that surface can come out to, right? That's my tolerance zone. Now, I guess people say, well, why not just use a plus or minus? Well, first of all, plus or minus is for size. If I put plus or minus on here, now I have another plus or minus over here. Well, then what's the relationship of this one to that one? This is a plus or minus. That could have went like this. This one could be a plus or minus, looks like this. And plus, this is a, would it come out a little further? Well, this is a geometrics class. And if we're doing geometrics, we're going to use geometric tolerancing all the way around. And you're going to find out when we're going to do our tolerance stacks a little bit later, it's really critical that everything is in geometric tolerancing. This is a geometric class. That's why we're here. We're going to apply geometric tolerance to everything. It's a mathematical 3D engineering language. And that's our language. That's what we're going to use. We have standards on it, American standards, international standards on it. So you see what profile does is it replaces the plus or minus. The good thing about profile is it establishes a datum. You come from the high points. With plus or minus, it's sometimes not clear. If you had surfaces had a flatness on here, the minus would be checked in between the gap and a high point. So profile is very clear. Rest on the high points, come in and see where that surface is. So that's why I used a profile here. And you notice that I'm going to use profile on everything that we do here. All right, the next thing that I did was on the bottom here, you see I located where this surface is, and I said that had to be profiled within 4. I'm contacting on a datum surface, and then that surface has to fall within a band of 4. So basically, what is it? It's kind of like something like 500 plus or minus 2. But the plus or minus 2 doesn't come from a datum. This one here, it says establish the datum, come from the high points, and make sure that surface falls within a band. So I use profile. Remember how it works. We use profile to locate surfaces. We use position to locate holes and slots. See, when we located this hole, we used a position tolerance. When we want to locate surfaces, we use profile. We use plus or minus tolerancing for the size of things. You see, what size is that hole? I use a plus or minus. Other than that, that's the only plus or minus I have on here, right? This is not size. If this was a plate, you know, some stock that I was going to buy from a Ryerson Steel or Central or U.S. Steel, then I would come in and I could put a plus or minus on it. But this is an actual machine dimension here that I want that surface to fall within that zone. All right, so that's my profile. So I'm just going around here and we're looking at features and we're controlling them. All right, the next thing that I'm going to do is, you see this gap, this radius right here. This radius, what I did is put a profile on. I put 3 surfaces. So I have a profile on this one, I have a profile on this one, and a profile on this one. They're all basic dimensions, and then I put a profile. It would be exceedingly rare for me to ever put a position on a radius. Finding the centers of radiuses is very, very difficult to do. And so, you can find the center of a hole by inserting a pin into the hole, but finding the center of radius is very difficult. So if I have radiuses like this, I'm going to put a profile on it right away. As a matter of fact, if you think about it, that's really what I want anyway. When those parts come together here, see, when the next part comes together and that cable fits in, what I'm interested in is what's the smallest that thing can be and what's the largest that thing can be. You see what that is? It's really nice. It's a profile tolerance. It says that radius will be a 375 radius, and then it can come in by 2.5 and can come out by 2.5. And right there I can tell you what kind of squeeze I have on that cable, anything else. All right, let's take a look at another one. You're noticing how nice this profile is. All right, now everything else, I guess I'm getting tired. There's nothing else to do here. You notice as we get further and further along, now what I'm down here, as I say, well, unless otherwise specified, everything else is profiled within 20,000. So I have a large profile tolerance, and everything is covered with a profile tolerance. That's my largest, my tolerance. So that's what this does is profile within 20. That replaces, remember how we have 2 place decimals, 3 place decimals into the title block? That's gone now. What I do is I just apply this profile, and it says unless otherwise specified. Everything that I missed was not important. That's going to apply a profile tolerance of 20 thousandths to it. And that's relative to the datums too, the datums which were A, B, and C. All right, that's our solution to the part. Now, here's an example where I thought I would show you here. We have a new standard that's just out. It's called the ASME Y1441, and it's a standard that talks about tolerancing of models, or just a definition of models, CAD models. And this here is a drawing that, if you can see where we're going, that we would like to be able to apply tolerance to the model. And this is an example of how we would apply tolerance to the model. All of the basic dimensions, you say, where are all the dimensions on this part? Where all the dimensions are, you would see the CAD file for the math data. And we don't really need any dimensions anymore. The dimensions are all in the model. They're all basic. The only thing we will have is a few places we'll have the size. See the size of the hole? Everything else is basic. If you want to know what these dimensions, you want to know what that radius is, take a look in the model. And so what we're really interested here in doing is what's the tolerance? That's what's important. If manufacturing is going to make this part, they want to generally know how big it is, how much stock they're going to have, but their question is, what's the tolerance? How close to the tolerance? So it gives them an idea what's important, what they have to shoot for. So you notice how I called it off. You see that face over there? I called off, that says datum A, it's flat within 5. The 3 surfaces here, I called that off as datum B, and I had a profile there. That was the one we had. And this was the perpendicularity. Remember that face? We said perpendicular. And once we had that, then we located that surface. We said it had to be on that line or down 5 thousandths. And then this surface here, remember that flat surface there? You see I just ended in a dot. That's profiled within 4. That's profiled within 4 thousandths. And then that was the position tolerance we put on the holes. See, there's your position tolerance. And then let's see, what else did we do? I guess what else we did is we located this top surface. Remember? We said that that had a profile within 4, and then all around, all the rest of it, everything else that wasn't covered, all up around here and everything, that had a general tolerance, and that said that it was profiled within 20 thousandths. And that was all over then, you know. All right, so this here is give you an idea how you might tolerance a solid model. The Y14541 standard, Y1441 standard that I talked about. That document will tell you just how to apply the symbology. Actually, the tolerancing, you'll still have to look in the Y145 document. All right, this here is our assembly, and I think we met all the requirements of our assembly. Our 12 thousandths gap that we had across here. We had the 5 thousandths, that's why we put it here. Our gap over here. This here 12 thousandths gap here, though, let's make sure that that was covered. And you should have your final solution on this, and that should be, you should have this example that shows all the solutions. And what we're interested in doing is making sure that we have the right gap when we take the two parts and put them together. So what we need to do here is do a little tolerance stack to make sure that these two parts, when I take the mating part and I put it together, that we will get this gap of 12 thousandths, that I did this correctly. So the dimensions or the geometric characteristics that we will have to watch for that gap over there will be this one up on top, this datum, that flatness, and this one where the arrows are pointing. That's what we'll have to watch. So let's do that. Let's take a look at a tolerance stack form. Now this tolerance stack form will show you how to do a simple tolerance stack. And what we're interested in doing is finding that min-max gap across here. Now for some of you who have not had the stacks program, this might not be something that you'll be able to do. I'll show you how to do it, but this here is not really a review. I'm expecting that you have already had the geometric tolerancing stacks program. If you have not had the stacks program, then you might be able to get the workbook. And if you take a look at the workbook, you should be able to follow in there how to do a tolerance stack. If not, then maybe you just want to skip this part, or maybe just watch how we're going to go about doing it. All right? So what I would like to do is give you a few minutes, and I'm going to have you do this tolerance stack. Knowing of what we have so far, I want you to come in and compute what that difference is, and I'd like to show up on this tolerance and see if our tolerance stack up comes in and gives us our final result. So I'll tell you what, I'm going to give you a few minutes here again for you to do the problem, do that tolerance stack. I'd like to see your work over here. If you're going to do a tolerance stack, do the stack path, I want to see your stack path. So I'll give you a few minutes and come back and see how you did. Well, welcome back. We're looking at the solution to the grommet. We were doing a tolerance stack, and one of the first things that we had to do was let's take a look at our graphic here. This was our start. We had to label a start and a finish, and remember what we do is we always label from start to finish as plus X, and we're going to always start on the left-hand side. Now we're going to start on the left side. The first thing we have to do is go through our stack path. And the stack path, let's see, number 1, you notice there's my number 1. What I'm doing is I'm going from that face, from that inside face, I'm going to the outside. That's going to be the first one, right? Because remember how we do it's like the pot of gold here. You're at the start and you want to get to the finish. And how do you get there? You have to travel through the dimensions to be able to get you there. So I'm going to go first, what I'm going to do is I'm going to start with that feature. Then I'm going to go to that feature out here. That's going to be my vector number 1. Let's see, where's my vector number 2? Just looking at it, you can see the vector number 2 is going to come over to this face over here. Let's put that on. That's going to be my vector number 2. We're now coming to the front face of part number 2. And now vector number 3 is actually the bulkhead itself. Right? And it's not really a vector. What I'm doing is just identifying that feature. That's feature number 3. And then let's see, where's my next one? My next one is vector number 4. And vector number 4 is going to be the distance from that face into here. Now, once we have our stack circuit laid out, it's all laid out, the stack path, the next thing that we're going to do is transfer the data. Now, remember how this geometric tolerancing works. It's different than plus or minus. So if you haven't had that stacks program, let me just quickly review here how this thing is going to work. Remember how it works is that in this stack table, you're going to put in part number, and that's what it is you see there's grommet number 2. I labeled them too. This was number 2, this one here is number 1, so we could follow along. And number 1, that's the first one that we're looking at. And that's that feature right there. It's that feature. See our little arrow there pointing? It's that feature. And that feature. Now what we're going to do is we're going to talk about that feature. It's different than plus or minus tolerance. Remember, plus or minus, it said, what's that dimension? We're not interested in what that dimension is. Geometric tolerancing wants to know about that feature. See that feature right there. And what I'm going to do is I ask you these questions. I said, what's the distance of that feature, and what's the total tolerance on that feature? All right, so that feature, what is it? The distance is 0. That's where we're starting. So that's why in the distance column I have a 0. The next thing is the tolerance. What's the tolerance on that feature? Well, here I have a drawing of that one, and I made the geometrics a little bigger. And you see it had a tolerance of 4 at a profile. So that's where I got my total tolerance of 4. I don't use plus or minus. We're using total tolerance. So that's a tolerance of 4. Okay, so that was, see where the little arrow was pointing? Then we looked at that feature. All right, now if we looked at 1, vector 1 is going to have 1, and it's going to have a point 1.1. And the 1.1 is the other feature now. So that vector really composed of 2 features. So that feature now, that outside feature, now what we want to know is we want to know the distance of that feature, and we want to know the total tolerance of that feature, right? Because we're going from feature to feature to feature and finding out every feature, what's its distance and what its tolerance, and we're going to label that inside of our compartment. So what it is here, that was a basic dimension. The distance was 247. And you notice since we're going in the minus direction, we're going in the opposite direction of plus x, that's going to show up as a minus 247, and the total tolerance is 0. And why the total tolerance is 0? Because that's our datum, right? That's where we're starting from, or that's where everything comes from. It's really, that doesn't have anything to do with our stack. You're coming from the high points on that datum. The flatness doesn't come into play. You're coming from the high points. So it has a total tolerance of 0. All right, let's continue on our stack path. Well, let's see. There's our stack path now. And this one here is going to be number 2. Now, why it's number 2 is because we've already done that surface over there, right? That was the 1.1. So this vector number 2 composed of 2 features, that feature and that feature, but that feature was already done. We did that with the 1.1. So what we have now is we have that feature right there. You see what that little pokey arrow is pointing to right there? It's that feature. So let's take a look, that feature. Well, what's the distance? The distance of that feature, it's 500. So in this distance column, I say it was 500 away. Since it's in a positive direction, it shows up as plus 0.500. And the total tolerance is 4. And you see that? Now I have a total tolerance of 4 because that surface can be off within 4. So that surface there has a total tolerance of 4 thousandths. All right. Let's take a look at the next feature now. We've done 2. Now we're going to look at 3. Now 3, where we're at now is we're at the bulkhead itself. Now when you're looking at that bulkhead, the bulkhead is really not a vector, right? It's just the bulkhead, right? Because remember how this works is the feature. What's the tolerance on this feature? And what we're doing is we're contacting on the high points of that feature. Right, if we're contacting on the high points of that feature, that's my datum. What I did is I call that's 3, so it's not even a vector, it's just feature number 3. And what's the distance of that feature? Well, it contacts the same place as the 2 features, so it had a distance of 0 and a total tolerance of 0. I did not include the flatness on the bulkhead. And I thought that the possibility of the flatness on the bulkhead incurring into the stack up was really practically non-existent. The only way that that flatness could occur is that if the flatness on this thing actually went down a little bit, right, that means this part number 1 would have to fall inside of the hole, and number 2 would not fall inside of the hole to affect that gap. So in this case here, I did not include any flatness in my in my stack at all. If you thought you should have, well then you know how I explained in the stacks program. You just put it in and you say I added to flatness. We'd come up with a different result, but then in the end we could compare answers and see what the difference was and then do a negotiation on whether we do want to include that or not. But I did not include anything. All right, now what we're going to do is we're going to go to the next feature. The next feature here is going to be feature number 4, and that's the right-hand edge of part number 1. Now remember, this here is going to be flipped around, so the right-hand edge of part number 1, if we took that thing and we flipped it right around, is now going to be that face over there. And that's datum A face. Right? And if that's datum A face, you see that's contacts on the high points, the flatness on there. I thought that the flatness didn't have anything to do with it. So what I did is I looked at that face, feature number 4, and I said that I did not include any flatness. The distance was 0, and then the total tolerance was 0. Okay, let's continue on. And then feature number 4.1. And 4.1 now is the inside surface. That would be this inside surface, because remember this thing is flipped around. And that inside surface, it has a distance, and it has a distance of 247. We're going in a minus direction, so it show up as a minus tolerance. And then my total tolerance was 4,000. So I put in my total of 4. Then you remember the rest of it here is just mechanical. What we're going to do is we total up everything in the distance column algebraically, watching for sign. We come up with a total of 6. And the total tolerance, you know, comes up with a total of 12. And when it says a total of 12, what that means is plus or minus 6. I put the little slash, and that means that it's plus or minus 6. So I'm kind of computing the min and max. I then just compute that, and it comes into a minimum of 0 and a maximum of 12,000. So that met our criteria. Remember on the design drawing, we had to have from 0 to 12. So that gives you a little idea how we would do the tolerance stack. And like I said, if you're not familiar with the tolerance stacks, you might be able to take a look at that stacks workbook, and that will help you understand what we did. All right. What's next here is this is our solution, and this is our part. What I'd like to do is to just talk about the solution. You have the solution in front of you, and maybe a little bit how you would inspect the part. Not that we have to go in and inspect the parts, but just generally, how would they go about this? What would they do? Now, you remember what our datums were. I don't have to do this over again, but A, and then this here was datum B, and this one was datum C. So let's take a look at our models here. The models. This here is our part. And what I'd like to do is explain a little bit how we would check the part if we were using angle plate, surface plate. Now we might use a coordinate measuring machine. I'll talk about that also. But sometimes if you can actually see the principles, how it's done. Remember what datum A was. Datum A was this back face, so they would probably bring it up against the angle plate. If they brought it up against the angle plate, you see it's contacting on the high points. Now we have to line it up in this direction. What they might use is a gauge block. This is a gauge block. We sometimes call them a 1, 2, 3 block. It's supposed to be theoretically exact. They have tolerance, but it's within gauge tolerance. I might take the angle plate. Remember how this angle plate is 90 degrees. Any way you turn it, 90 degrees. We know it's calibrated on a periodic basis. We know that it's good. So I might take this part, turn it sideways here, bring it down to this top surface. It's lined up on the gauge block now. You notice that basically on this one, it's a simple one. I have primary datum, and I'm bringing it down to my secondary datum. It's locked on. And what I'll do is I'll raise mine up here a little bit. And the reason I'll raise it up a little bit so I can get a clamp on. And that's now lined up to my primary datum. Now once the thing is lined up to my secondary datum, you notice now when I'm going to be able to make any measurements on here, that would be pretty straightforward. Making any measurements in this direction, you see I just take my height gauge. Well, first of all, I guess up and down, I could take all my measurements in this direction. You see with my height gauge here, I take my height gauge, set it up. I can get my 0 off the plate. You see, remember all those dimensions? Remember where we were checking this surface here? I think that surface had to be within 500, and it had to be a plus or minus, not a plus or minus, but a profile of 4. Then we came over to this surface, and we would come in and we were indicating this surface. That had to be within a zone. See what I'm doing is I'm resting on the high points. I'm coming to see if that falls inside of the tolerance zone. And then to be able to measure in this direction, remember 90 degrees, I could come in, take my indicator, I have my needle, And this here is a dial test indicator. It's a dial test indicator. You notice as I push it down or I push it up, it gives me a reading. I can get where 0 is. I come in, get that bottom surface. And when I read about that bottom surface, what is it? That was the profile. All of those surfaces have to fall within that band of 5. All 3 of them have to fall within. Once I got that, I can make any measurements that I need to in this direction, right? I could go in and I could measure where the hole was. I could come in and I could measure points across here. Now, if I wanted to measure any other direction, you see all I do is I move 90 degrees. When I move 90 degrees, I'll come in and I'll get a 0 on this face over here. Remember, that was my datum in this direction. And when I run my needle across here, do you notice if my needle was moving, that needle couldn't move any more than 5 thousandths. That was my perpendicularity. And then from there, I can make any measurements I need to in this direction to center the hole and do my positions in this direction. So you notice how important it is to have a datum reference frame. If you have a datum reference frame, everybody sets the part up and measured it exactly the same way. Now, actually how you're going to, I guess supposedly I could just come in and measure some certain things with calipers. This geometric tolerancing doesn't tell you how to measure anything. It just tells you in theory what it's supposed to look like. And then how you're going to measure it, how much risk you want to take, what kind of procedure. So that's up to the quality department to make their decisions, what they're going to do. Now, if you're going to measure this thing with a coordinate measuring machine, probably what they would do on something like that, well, I don't know, they might come in and just lay the thing down on the table. If they came down on the table, I might come in and I would touch my 0 on this back face, establish a plane. Once I establish a plane, now I have to come in with my secondary datum. Probably what they would do to establish the secondary datum, come in and touch the surface a minimum of 2 points. You probably have to touch more than 2 points and establish a plane, and then be able to touch, a minimum of 1 point and be able to establish a plane. And then once they did that, they would find an origin just like we did here a minute ago on the angle plate and surface plate. Now, just be aware here. Let me show you on our graphic. Let's just go back to the graphic for a minute. And on the graphic, I'd like to show you just some things. If they come in with a coordinate measure machine and they were to come in and they were to just touch 2 points, by just touching 2 points, you wouldn't know much about that surface if they just touched 2. So they would probably have to touch a number of points on that surface. And when they did, they would come in and find out it fell inside of a tolerance zone, right? If they touch more than 2 points, they're going to get, a number of points. You're going to collect data on this surface, and they collect that data. Now remember, what they're supposed to do is they're supposed to come in and move to the high points, right? Because that's what the datum is. Remember, that's what the designer is calling off. So they would have to come in, and once they found that that surface fell within that profile of 5, then they move to the high points and they establish the first plane. Same thing with the secondary datum. When they come in and touch it, they could touch it 1, but if that surface actually looks something like this, where are they touching? So they would have to touch a number of points. Once they got it, they would find where it was and then translate and come to the highest points, right? Translate it over to the highest points, and that's their origin. So once they had their origin, they're home free. Now they're just going to come in and start making measurements. Remember the position tolerance? We've done this in the fundamentals program, so I need not go over that again, but basically in this direction they have an x equals 0. In y direction they have a 625. They would come in and find out how much it's in x, how much it's in y, and if they had to, trig it out and find out what kind of diameter it is. They could check this hole. You notice in order to check this radius, that would be a simple thing. There's their origin. They would move down 375, reset an origin, and then come in and probe that surface and make sure it fell within a zone. They could come down and check this. Oh, for example, this outside, see within profile within 20. How many points they're going to check? Probably if it's a lot of tolerance, they're probably going to check less. If it's a tighter tolerance, they're going to check more. It depends on the process, how the part was made. Is this the first part you're checking, the 100th part you're making? What's the tolerance? Who made the part? What do you know about the part? But one way they could do it would be they have their origin. They could come down 2.250, come down, and then they would touch spots. And as they touch spots, they're going to find out how much they're off that spot. And sometimes they do it like a whisker diagram, that if they touch a spot over here, that's supposed to be 0, and they find out, well, it came in at +5. Then they're going to check another spot, and they said, well, that one come in at -2, right? And then if I did that, I can come in as a designer, I can collect that data even from the coordinate measuring machine, input, and I can connect the dots and I can actually draw you the picture what the part is supposed to look like. See that outside radius? They could come over and set their 0 on the basic dimensions. See that 1.625? They're going to come at that 1 inch to come over to that spot. Then they could come in and they could probe where this surface is. If they want to find out where this surface is, they could do the same thing. Set their 0 over here and then probe that surface. Right? That's how they're going to be looking at it. So the profile tolerance are just seeing how much it's off its spot. Right? All right, that gives you a little idea, a little insight into the inspection. I talked much more about the inspection in the fundamentals program. This one here is really an applications program, but I wanted to, some of you maybe have not had any geometrics, or you've had the program from someone else, or you've just read it from books and you haven't had the fundamentals. Sometimes you like to jump right in the application. You think you can do it because you have some background. So just a little bit of a review here. This isn't a full-blown program on the fundamentals and inspection and verification. This is just some general roundabout knowledge that you should have. And we're going to go on because sometimes people say, do we want to put geometrics on everything? Yes, we want to put it on everything. We want to completely define our product. We want it to be crystal clear what our product is supposed to look like. All right, let's go on. And to go on, let's take a look at our part here now. This is the part that's in the assembly. And you notice it's bolted up to the bulkhead. And if it's bolted up to the bulkhead, remember how I said that it worked. You take this part, you do 2 parts, you put them together around the cables, and you tighten up the bolts. And that's what holds this part together so it can't come apart. So you will push the 2 parts together, tighten up the bolts, and it holds it up tight. But now what would happen if the bolts were to loosen up? Because you see these holes? Those holes had a position tolerance on them, and they had maximum material on those holes also. So if they did, what could happen there? Well, let's take a look what could happen. You see the holes in the actual part could move around the bolts. And they could move to the right, they could move to the left like that. And if they move to the right or left, it's possible that if those bolts, if the nuts and the bolts ever loosened up, the 2 parts could come apart like that. Now they would only come apart by the amount of the looseness in the bolt and the clearance in the bolt here. That's how much. But what they're worried about here is what is that max gap? What is the worst that they could ever come apart, if they were to ever come apart? In other words, what we'd like to do is calculate that max gap when the 2 parts are pulled apart to their max while the bolts are still in the hole. Now, how would we go about calculating something like that? Because that might be a requirement. And we kind of talked about this in the stacks program, so if you've already had the stacks program, you should be thinking about this. Some wheels ought to be turning in your head. You say, well, how the heck would I do that? Now, you could probably do that by way of a vector stack, but that would be pretty complicated to do, and you'd have to have a stack path and everything else. And sometimes, we just kind of do it by the seat of our pants. We look at it and we say, well, how much would I have here without going into a real involved stack? So you notice that the way that I would approach something like this, if I was looking at that worst case, that worst gap, if you bolted up, it could come apart. Is what I would do is I would take a look at these holes. You see I have that bolt right there? And if I have that bolt here that's coming through, that's a loose bolt that's coming through, and I took these holes, and these holes came in at their largest size, and if they were at their largest size and this one moved over this way, and this was at its largest size and it moved over this way, then the parts could come apart. So if I could do this, if I could find out what that outer boundary of that hole was, you see that clearance hole there? The largest that hole could get going this way, and the largest that hole could go coming this way, right? Because it's really going to happen up here. The largest that that's probably rather than down here. This is what's going to happen. Let me show you the details. Sometimes people say that they'll actually open up and rotate, but they really won't rotate. Let me show you the model here again. And here's the model. You see, if they were put together, see, remember how these go together? They almost fit like a hand and a glove. Remember, I had this surface here matches up to this surface here. So when the 2 parts come together, they're coming together like this. And if I try to rotate them like this, they will not rotate. And the reason they won't rotate is, you see how the little dovetail, this piece slips in here, and it does exactly the same thing on the other side. So could rotate a little bit, I guess. But, and we could do an orientation stack. If you've had the stacks program, you know how to do that orientation stack. But to keep this simple, what's basically going to happen is they're going to move apart like this. So let's take a look at how we would calculate that. Well, the first thing, let's take a look back at our graphic then. I have this hole, and I would take the outer boundary of that hole. Then I'm also going to look at that, remember this gap over here. Remember we had a profile tolerance on this one and we had a profile tolerance on that one. That's something that we also have to include in the stack. So let's take a look at our part here. And what we're going to do is we're going to take a look at that hole. And what I'm going to do is I'm going to take the largest hole that I could ever get. I'm going to go to the outer boundary. And the outer boundary on that hole, you remember we had some formulas for that. If you have a hole that was positioned at maximum material condition and you're looking for the boundary, remember the boundary formulas? The boundary formulas is you would take the least material. You take the least material, and the least material is 406 plus 15. That would be 421. And then you take total size tolerance, and the total size tolerance is 17 plus the geotol. Plus the geotol is 29. I total them all up, and the outer boundary is 467. And remember what I mean by the outer boundary here is that you're going to take, what that says is the larger the hole gets, right? So how much position this hole can have? It can have 29, but it can have 29 position when it's at maximum material condition, at the smallest hole. If this hole gets bigger by 17, it can move another 17. So we figured out the worst case outer boundary. And just let me show you what that outer boundary here, how it works. The outer boundary would be like this. Remember when you're looking at the outer boundary in that hole, if you had this hole and it had a positional tolerance of 29, there's your 29,000 position. Sometimes the hole could be here, right? And sometimes the hole could be here. And then if the hole gets bigger, it could be off more, and it could be off more like this. And what that outer boundary, this outer boundary calculation here that we have done, that 467 that we've come up with, is the biggest hole swing this way, and it would be the biggest hole swing this way. And it's really two parts. So if I took a half of an OB and a half of an OB, I have an old OB. And that's how much it's going to move around on that bolt. So looking back at our graphics then, this is what I come up with, is the worst case outer boundary was 467. And then I have the inner boundary on the bolt. And I didn't really take any bolt tolerance in consideration. Probably in a real example I should have, but just to make it simple, I said we had a 375 bolt. So if I had a 375 bolt, that's the inner boundary of the bolt, and that's the outer boundary of the hole, I would have 92 thousandths clearance. Now if I had 92 thousandths clearance, that's how much those things could pull apart at their worst case. But then on top of it, you remember what we had, is we had a profile tolerance on this one within 5, and we had a profile tolerance on this one within 5. So I'd have to include that 5 and that 5 across there. That's where I included a 10, so I had a 0.92, and then plus the two profiles, and then I had a max gap of 0.102. That's the max gap that you could ever have when those were pulled apart. And that's a real practical example. You know, just a quick one. If you know those stacks from the earlier program, you can see how quick that, you can make quick work out of that, something like that. So that's our problem. So this is our final solution. Final solution to the problem. You can review that, view that with other people there in your group, and I'll tell you what. If you finish this one, we're getting ready. We're going to move on to the next one. We're going to move on to unit number 2. So hope you enjoyed that one. We're going to have see more of the same. This example with the grommet, all we did was worked with surfaces. We worked with plane surfaces, right? And there weren't any MMC on any datums. The next problem we're going to have, we're going to apply MMC to datums. So it's going to go on a little bit more. And if you need a review, what I would do is go back and review that fundamentals workbook, because we're not going to do too much of a review. We're going right in and we're going to start applying this tolerancing. So we'll see you for the next unit, the powder case. See you then.